Good morning students. Today we are going to continue behavior of gases remaining part. Okay, already we have completed Boyle's law, Charles law, Montan's law and Avogadro's law and some of the application parts in ideal gas equation, right? So today we are going to complete in this video Dalton's law of partial pressures and Graham's law of diffusion. Okay, let's start our video today with Dalton's law of partial pressures. See here. Before going to the Dalton's law of partial pressures, what is partial pressure we should know. See, what is meant by partial pressure? If you take one gas, that gas you are taking in a container, that gas itself exerts some pressure, right? That pressure is called partial pressure of that gas. Means the gas exerted by the individual gas is called partial pressure. The pressure exerted by the individual gas itself, it is called partial pressure. Okay, so what is mainly this Dalton's law of partial pressure dealing with? Here in a container, if you are taking two or more gases if you are taking, and here the condition, those gases are not supposed to be reacted to each other, means some non-reactive gases are taking in a container, the total pressure exerted in the container will be equal to sum of the partial pressures of the individual gases present in the container, right? So this one we can explain through some examples. Let us see here, they given about the partial pressure. Partial pressure is nothing but the amount of gas is present in a container at definite temperature and then pressure exerted by it is called its partial pressure. That one simply we can say the pressure exerted by the gas at constant and temperature and pressure itself is called a partial pressure of that gas, right? So to measure this one, see generally already while starting the behavior of gases we have discussed about the barometer and manometer. Barometer is nothing but to measure the pressure, right? Pressure of the atmosphere. To measure the pressure of the gas we use the manometer, and here this barometer and manometer cannot measure the pressure individual pressure, means partial pressure. Okay, only they can measure, this manometer can measure the pressure of that container, means in that gas, the combined gas whatever we have, that gas's pressure it can be, but the individual pressure of the gas cannot be measured by using any barometer or manometer. Okay, let us see what is the Dalton's law. That is what I said. Dalton's law means if you take one container, I will take here one container. In this container we have mixed A and B, right? We get A and B. I am taking those A and B as the examples. So A and B. Then you close this with some lid. Here A itself it has some partial pressure because it is an A. That gas has itself some individual pressure. That pressure is called partial pressure of A. And at the same time B, if you consider, B itself it has some individual pressure, that is called B, means partial pressure of B. Here after the mixing, and also here one condition in Dalton's law, this A and B are not supposed to react. If they react they will form a new product, right? So two non-reactive gases are kept in a container. The total pressure exerted by this container will be equals to sum of its partial pressures. Sum of its partial pressure. So the total pressure exerted by this container will be equals to sum of its partial pressures. Okay, this is the Dalton's law. Total pressure exerted by the gaseous mixture equal to sum of its partial pressures. Partial pressures here we considered as PA and PB, and we defined what is partial pressure. The pressure exerted by the individual gas. PT means total pressure of the container, means A plus B combinedly in the container how much pressure it is taking, that is gives the total pressure. So PT equal to sigma Pn, means not only two components, not only A and B, you can take so many components, but all the total pressure exerted by the container will be equal to sum of its individual pressures, right. So simply we can write PT means total pressure equal to sigma Pn. Sigma indicates the addition, Pn means you can take so many number of gases like. So this is simply indicates the Dalton's law of partial pressures, right. So here calculation of partial pressures. How to calculate the partial pressures? Here these partial pressures depends upon some of the mole fraction like. See, let's gases mixtures exert some pressure means PT. Gases mixture, whatever the gases, suppose we are taking 1, 2, 3 and so on, n type of gases we are taking, the total pressure exerted by that gas will be equal to sum of its partial pressures, P1 plus P2 plus P3 and so on, Pn, right. So what about the P1? This P1 indicates the partial pressure of that first gas. How to calculate that partial pressure? Partial pressure is nothing but nRT by V, that is what ideal gas equation, PV equal to nRT, right. This is only no ideal gas equation, PV equal to nRT, that one simply we want pressure, now we are writing as nRT by V. So we are taking 1 for first gas, number of moles means N1 is different, the remaining volume, temperature and are all same, that's why P1 equal to N1 RT by V. If you want to calculate for partial pressure of the second gas, then nR2 by V. P3 N3 RT by V. Only number of moles are changing, not their conditions, means their temperature is not changing. How much volume we are taking first gas, second gas also we are taking the same volume. So at constant temperature, for the given temperature and volume conditions, the pressure of the gas we are changing only number of moles. P1 gas added 2 moles, then P2 gas added 3 moles, P4 gas added 4 moles. So number of moles can be changes, but their conditions are not changing. That's why here RT by V we consider as the constant. Only number of moles is changing. So totally what we can write, total pressure, substituting the total pressure this P1, P2, P3 values, then N1 RT by V plus N2 RT by V plus N3 RT by V, right. So PT equal to, in this total in common, RT by V is common, right. So take common that RT by V, then you will get N1 plus N2 plus N3, right. So total pressure is equals to N1 plus N2 plus N3, means number of moles of first gas plus second gas plus third gas into RT by V. So P1 by PT, if you want to calculate the partial pressure for the first gas, then you have to take P1 by PT equal to N1 by total. If you want to calculate for P2, then N2 means total, N2 by N1 plus N2 plus N3 into PT means total pressure. What is that N1 by N1 plus? That is what mole fraction. Mole fraction means nothing but the mole fraction of solute plus mole fraction of solution. Solvent gives you mole fraction of this solution. Here this N1 plus N2 plus N3 overall we will take as a gaseous mixture, for which you want to calculate the partial pressure, that one we will take, that number of moles by N1 plus N2 plus N3. So total P1 means partial pressure of the first gas to calculate. PT means total pressure into mole fraction. X1 means for first gas. If you want to calculate partial pressure for second gas, then the formula will be P2 equal to total pressure PT into mole fraction of second gas, means X2. What is the formula for that mole fraction X2? X2 equal to N2 by N1 plus N2 plus N3. If you want to take mole fraction for third gas, then formula will be N3 by N1 plus N2 plus N3, right. So this is the formula to calculate the mole fraction or partial pressures by using the mole fractions, right. See, here the mole fraction is defined as the ratio of number of moles of one component by total number of moles of the solution, or mixture, right? Here that is the definition for mole fraction. And also here the main condition for the Dalton's law of partial pressure is whatever the gases mixture we are taking, those gases should be non-reactable. They should be non-reactive gases. Those gases are not supposed to react itself, right? So that gases mixtures examples are given here. Dalton's law of partial pressure is applicable only when it is applicable when you are taking in a container the non-reactable gases, right? So when only for non-reacting gases. What are those non-reacting gases? They have given some example. N2 plus O2 we can consider as a non-reactive gases like, and also CO plus N2 can consider as a non-reactive gas. CO plus CO2, carbon dioxide and carbon monoxide, these are examples for non-reactive gases mixtures. And we have some more examples in that for which one the Dalton's law of partial pressures is not applicable. Not applicable means what? Those gases are reactive to each other. Here the example, NO plus O2, both are reactive to each other. If you take those two in one container, they will react and they will form a new product. Then we cannot calculate the individual partial pressures for those gases, right? So Dalton's law of partial pressure will not be applicable for such type of gases. One more example, H2 plus Cl2. If you take H2 plus Cl2, it will form HCl, hydrochloric acid, right? Then HCl you cannot calculate then individual gases of partial pressure H2 and Cl2 like. And one more thing, NH3 plus HCl, if you take this combination, immediately in the container it forms NH4Cl, ammonium chloride. Then also Dalton's law of partial pressure is not applicable. Graham's law of diffusion, right? So Graham's law of diffusion. What is Graham's law of diffusion? Before going to the Graham's law of diffusion, first of all we should know what is diffusion means. Diffusion, see, if you are taking one spray bottle, you just press that spray, then that spray smell will be occupied throughout the room, right? That is nothing but called, in that the gases present inside the spray bottle are under high pressure. Whenever we are pressing them, they will come to the high pressure region to low pressure region. That is called diffusion. Even we can take the example of the balloon. If you bulge the balloon and so the particles present inside the balloon, the air present inside the balloon is under high pressure. Whenever we are keeping a small hole to that balloon, it makes some sound and it comes outside. Or otherwise cycle tire which is puncture, then we will make a sound, means that if you make a small hole, the whatever the gas present inside the tire, it comes outside slowly making some sound. That is nothing but called diffusion. It is traveling from high pressure region to the low pressure region, it is coming out. That is called diffusion. Let us see what is the Graham's law of diffusion of the gases. Gases can diffuse from one place to other. How the perfume spreads into the room when the perfume bottle is opened. The same example what we explained here. So the diffusion is nothing but the gases particles are traveling from high pressure region to the low pressure region. Okay, high pressure means when we are closing that and we are keeping in a container with a closed lid, then that is under high pressure, those molecules. When we open the lid, they will come from high pressure region to low pressure region. They can occupy so much space. There is no pressure. When the more volume, no pressure, right? That is what Boyle's law. Volume is inversely proportional to the pressure. That is nothing but high volume, more volume means more space it can occupy, it shows less pressure, right? So based on this Graham's law of diffusion of gases, they are taking some example, that is NH3, H2S and SO2. They have done some activity how this Graham's law of diffusion is works. Let us see here. They have taken one activity, in that we have taken example of NH3 and Cl, right? NH3 and Cl. So they have taken one long tube. And they closed with some lids over two sides of the tube. At one side of the tube there is a NH3 which is dipped into the NH3, that cotton wool is present. Another side some cotton wool is there which is dipped in HCl, right, which is dipped in HCl. Remaining part of the tube in the middle is the empty. So we are taking some time and the procedure is started. What happened? So this NH3 should react with HCl and it should form a white color cloud type of NH4Cl inside the tube, right. So where is that white cloud of NH4Cl is formed? Where that white color NH4Cl is formed, they observed in this experiment. So where we observed, that is near to the HCl, that is nearer to the HCl cotton wool, far from the NH3 cotton wool. That is nothing but by comparing HCl, NH3 is travelled more distance. NH3 is diffused more than the HCl. That's why NH3 is travelled more distance. When HCl travelled L2, NH3 travelled L1 length, means L1 distance it is travelled. Why the diffusion is faster in NH3 when compared with the HCl is nothing but its molecular weight or its density. What is calculate the NH3 molecular weight? Nitrogen it is 14, 3 hydrogens means 3, so total NH3's molecular weight is 17. Whereas come to the HCl, hydrogen is 1 but chlorine is 35.5, so molecular weight is 36.5. NH3 is 17 and HCl is 36.5, so less molecular weight gives more diffusion of the gas. So the diffusion, the rate of diffusion depends upon the molecular weight or density of the given gas. This is the Graham's law of diffusion. What Graham wants to explain based on this activity, he has done experiment this where the white cloud of NH4Cl is forming nearer to the HCl, because HCl travelled less. While HCl travelling L2 distance, NH3 is travelled L1 distance, which is more than the L2. That is nothing but the gaseous particles which has the less molecular weight or lower density can travel more, means can diffuse more. The rate of diffusion of the gases are inversely proportional to square root of its density. So through this experiment he brought one relationship for the between the rate of diffusion and the density is nothing but R is proportional to, means rate R is nothing but here rate of diffusion. Rate of diffusion is directly proportional to square root of 1 by D. Otherwise you can write R is directly proportional to 1 by square root of its density. Density is more is nothing but molecular weight is also more. So obviously we can write the same formula with rate of diffusion is directly proportional to square root of its molecular weight of the particular gas. For which gas we want to calculate rate of diffusion? That's molecular weight, that gas is density. So when we are taking at two different conditions, this one we can write R1 by R2, means rate of diffusion of first one by rate of diffusion of second gas is square root of its D2 by D1 or square root of its M2 by M1. Here M2 represents the molecular weight. So that is what R1 by R2 equal to square root of its density. R1 by R2 equal to square root of its molecular weights M2 by M1. So what is the Graham's law of diffusion? Rate of diffusion is directly proportional to square root of 1 by its density. 1 by root density also we can take, right? So totally he generalized the given reaction. So whatever he observed based on density and molecular weight, he generalized some relation with the rate of diffusion of gases and the properties of the gas. See, so when this law is used to volume and density also he has taken. So R equal to V1 by T diffuses faster, which has the less molecular weight, that diffuses the faster. So he brought this relation also, rate of diffusion is equal to the volume of the gas escaping in particular time. So V by T. When we are taking for two different gases, R1 by R2 equal to V1 by T1, V2 by T2, that one we can write as V1 by T1 into T2 by V2. So we can write V1 by V2 into T2 by T1. This is the relation. So overall the relations are this. R1 by R2 equal to V1 by T1 by V2 by T2 equal to square root of its D2 by D1 square root of its M2 by M1. So this is the Graham's law of diffusion. What is basically Graham's explained that diffusion depends upon the density of the gas or molecular weight of the gas. Molecular weight is less, density rate is more, diffusion's rate is more. Rate of diffusion is inversely proportional to its molecular weight or its density with square root, right? So this is Graham's law of diffusion, right? Let us see one problem based on Graham's law of diffusion. See, the rate of diffusion of methane at a given temperature is twice that of a gas X. The molecular weight of X is, so he is asking the comparison of rate of diffusion between the two gases, right? So what is the formula we know for rate of diffusion? Rate of diffusion is inversely proportional to square root of its density or inversely proportional to square root of its molecular weight. But in the problem they are talking about molecular weight, so I am taking the relation directly for the molecular weight. Then rate is molecular weight. So this one, when we are comparing for two gases, we can take R1 by R2 equal to root of M2 by M1. Now this is the relation between the rate of diffusion and molecular weight. Now using this formula we have to solve this problem. Okay, the rate of diffusion of methane at a given temperature is twice that of rate of diffusion of gas X. Means first one you consider as X, second one you consider as methane or CH4. Otherwise first gas you consider as RCH4. Suppose RCH4 rate of diffusion is considered as A. Then rate of diffusion of X, that is what given. Rate of diffusion of methane at a given temperature is twice that of gas X. So Rx you have to consider as A. Then rate of diffusion of 2CH4 means rate of diffusion of methane will be 2A, twice to that of this X. And we don't know the molecular weight of X, that is what we have to calculate. Then molecular weight of CH4 equal to, for one carbon it is 12, for 4 hydrogens it is 4, so 12 plus 4 it is 16, so it is 16. Now these values you should substitute in the given problem, right? So if you take RCH4 by Rx equal to root of Mx by MCH4, R1 by R2 equal to root of M2 by M1, this is the formula. So what is the molecular weight we want? RCH4 is how much? 2A. Then what about RxA, which is equal to root of Mx we don't know, but molecular weight of CH4 we know, that is 16. So 2 get cancelled. Then it will be, I am writing over here. So 2 equal to root of Mx by 16. This root 16, this root belongs to Mx and 16. So I will write root Mx equal to 2 into root 16 is nothing but 4. So 2 into 4 equal to 8. Root Mx is 8. But we want Mx only. So we want only Mx. Then Mx equal to 8 power 1 by 2. So how can we write that is 2 square into 2 power 1 by 2, 1 by 2. So we will get some, if you calculate this one, 2 root 2, that is nothing but 2 into root 2 value 1.414. If you substitute that, we will get the value, right? So this is the process. First what is the data given and which formula we have to use. Based on that we have to do this one. You can get the doubt. How we have to take? Either we have to take Rx by RCH4. We can do even like that also. Let us see. Rx is A by RCH4 is 2A. Then which is equal to 16 by Mx. A get cancelled. Then root Mx equal to 2 into root 16 means 4. That is also 4 2s are 8. Root Mx is 8. So Mx means molecular weight is root 8. So that root 8 we have to calculate. 2 root 2 like we can write, right? 2 root 2 value is how much? 2 into root 2 means 1.414. You can substitute and you can get the value. So this is the process to do the problems based on diffusion. Not only on molecular weight, they can ask related to the volume and they can ask related to the density also. Same like this data we have to write and we have to solve this problem, right? Okay. So this is the Graham's law of diffusion. What are the relative? One more problem we can see. What are the relative rates of diffusion of hydrogen and oxygen gases? So here they given two gases. They are asking the relative rates. Relative rates is nothing but asking the relation. So first of all, relative rates is nothing of diffusion of hydrogen and oxygen. So first asking for RH2 by RO2 equal to root of MO2 by MH2. This will give the relation. Molecular weight of O2 is how much? For one oxygen it is 16. O2 means 2 oxygen, so its molecular weight is 32 by, for one hydrogen it is 1, so H2 for it is 2. So 2 16s are 32. So RH2 by RO2 equal to root 16 means 4. So 4 by 1. So therefore RH2 equal to 4RO2. The ratio is, what is the relative rates of diffusion of hydrogen and oxygen? Hydrogen will diffuse 4 times to that of oxygen, because hydrogen is the very lesser, right? Hydrogen is the very lesser. It diffuses faster than the oxygen, right? So how oxygen will spread? That 4 times hydrogen. One time oxygen if you move, hydrogen can move 4 times faster than that. That is the relation between the hydrogen and oxygen between the diffusion, right? So this is about the Graham's law of diffusion and Dalton's law of partial pressures, right? Thank you so much.